I want to welcome you to the G. Brown Goode Lecture. We're joined here today by colleagues from across the country who will be watching the webcast this afternoon. In particular, I'd like to mention two groups that will be joining us that have a particular relationship with the Smithsonian. First is announcements were sent to all of the Smithsonian affiliates across the nation. And we know from the last affiliates conference which was held here that many of the affiliate members and our colleagues have watched the previous lectures and have enjoyed being part of this discussion. We also invited the Teachers of the Year from the 57 different jurisdictions, and many of you participated in training those teachers earlier this year so that they could go out and be ambassadors for the Smithsonian. And they also received information about this, and we're going to follow up with follow-up discussions with them as well. So I'd like to welcome those two groups as well as other colleagues. This lecture represents a collaboration between the Smithsonian Center for Education and Museum Studies and the Science Education Department at Harvard's Smithsonian Center for Astrophysics. And Matt Schneps is here with us as director at that unit with us today. In earlier conversations, we used to talk with Matt about a lot of the education work they're doing at Harvard, and we wanted to find a way to also make more of the people here in the Washington, D.C. museums aware of it. And so the lecture today with Carolyn Maher, you're going to notice on the back of your program that there's a website, and you can see on that website it makes visible some of that collaboration. Through this series, named after the Smithsonian's earliest proponent of museums as educational institutions, the Smithsonian and other museum staff can keep abreast of the emerging developments in education pertaining to aspects of their work, from exhibit design to outreach to the schools. This first lecture in the series is the first lecture in a series on 21st century skills. Recent reports from foundations, government agencies, and universities argue that today's students are not skilled in critical thinking skills that they need in order to be citizens and workers, and some claim that this jeopardizes America's competitive edge in the 21st century. So you now see these essential skills such as critical thinking, problem solving, collaboration are often referred in the literature to 21st century skills, as 21st century skills. In this series, researchers from universities and museums will examine critical thinking, problem-solving, collaboration, and other skills necessary for success in the 21st century, and the roles that museums and informal learning environments can play in developing these skills for learners of all ages. The presentation today is Fostering Critical Thinking in Schools and Museums. Our lecturer is Dr. Carolyn Maher, Professor of Learning and Teaching at Rutgers University and Director of the Robert B. Long Davis Institute for Learning. Dr. Maher will present results from a remarkable long-term study, now in its 20th year, that follows a group of students as they grow from first grade through college and beyond, to trace how their abilities for critical thinking grow and evolve. Looking at an example drawn from children's thinking in mathematics, her study demonstrates that when children's capacities for critical thinking are honored, even modest opportunities for learning can make a lasting impact, build self-esteem, and provide tools children can take with them to achieve productive careers. This research suggests possibilities as to the role and potential impact of museums and informal education programs by looking at the difference that powerful, engaging, but often short interventions can make. Her presentation will be followed by a discussion that will explore critical thinking in museums, parallels between critical thinking and contexts important to museums, and Professor Maher's research in mathematics to investigate how the ideas presented might be built upon or not in museum contexts, fostering critical thinking skills. Rebecca Shulman Herz will introduce the program today, providing a framework for thinking about Carolyn's work in our museum context. Rebecca is the Senior Education Manager at the Solomon R. Guggenheim Museum, and she is the guest editor of the summer 2007 issue of the Journal of Museum Education that focuses on critical thinking in museums. After the lecture, she will talk about the impact of museum-based school programs on critical thinking skills and why museums are creating and investigating programs that aim to develop critical thinking skills, and what research tells us about the effectiveness of these programs. This lecture, as I mentioned earlier, will be webcast, and it will also be made available on the Museum Studies website, and that's museumstudies.si.edu. Finally, I'd like to acknowledge some people in the audience who worked very hard on this program as well. Matt Schneps, who suggested the program and collaborated on its development, Nancy Fuller, who facilitated its development and shepherded it through, and Bruce Craig, who manages the lecture series. Thank you for your efforts that resulted in the program today. Finally, I had the opportunity to have lunch with our speakers today, and I found it so enjoyable and I learned so much. I'm looking even more forward to the lecture today and to the questions and discussion that follows. With that, I'd like to introduce Rebecca.
Hi. In a minute, Carolyn Maher is going to present her remarkable 20-year longitudinal study on the mathematical and critical thinking skills of students. And when she's done, I'll share a related study conducted by the Guggenheim Museum, and then share a few thoughts about the implications of all of these studies for our work in museums. But first, I want to think about why focus on critical thinking skills. What do we know about what these skills are? And why should museums care about teaching them? There are many different definitions of critical thinking, and here are a few. The first is from the Delphi Report, which is a 1990 publication of the American Philosophical Society. We understand critical thinking to be purposeful, self-regulatory judgment which results in interpretation, analysis, evaluation, and inference. The ideal critical thinker is habitually inquisitive, well-informed, trustful of reason, open-minded, flexible, fair-minded in evaluation, honest in facing personal biases, prudent in making judgments, willing to reconsider, clear about issues, orderly in complex matters, diligent in seeking relevant information, reasonable in the selection of criteria, focused in inquiry, and persistent in seeking results which are as precise as the subject and the circumstances of inquiry permit. Thus, educating good critical thinkers means working toward this ideal, which is asking quite a lot. The second definition I wanted to offer is from John Dewey, who calls this type of thinking reflective thought, and writes that reflective thought is active, persistent, and careful consideration of any belief or supposed form of knowledge in the light of the grounds that support it, and the further conclusions towards which it tends. I also wanted to throw out the idea of educators at Harvard's Project Zero, who put forth the idea of critical thinking not as a set of skills, but as a set of dispositions. Something that most people can do, but that many people don't do as often as they might, and to teach critical thinking is to foster these dispositions rather than to teach new skills. Given that educators can't even agree on what critical thinking is, why should it be important to museums and museum educators? Traditionally, our mission is to teach people about our collections and our exhibitions, and these collections and exhibitions are what make each museum unique and what draws visitors to them. Yet more and more museums market their programs as teaching critical thinking skills, often instead of teaching about objects or collections, and I suspect this marketing language mirrors internal conversations about goals, which also focus on transferable analytic skills. Here are a few possible reasons why, as I've thought about it. The first is that in an age in which information is easily available and overwhelming in quantity, educators in general are shifting toward a focus on skills rather than information. Second, a focus on critical thinking helps us claim that our exhibitions are relevant for school groups, whether or not they fit with a specific curriculum focus. This in turn allows us to lead conversations authentic to the art or other objects, rather than trying to shoehorn student conversations, for example, about an exhibition of Jackson Pollock's work into the context of the United States in the mid-20th century. The third is that focusing on critical thinking skills rather than content potentially shifts the dynamic between the curatorial and the education department, rendering the education department less reliant on information held by curators. I'm going to pause for a moment and ask everybody to think about your personal or institutional definition of critical thinking. What does critical thinking mean to you? Why is your institution setting critical thinking skills as an educational goal or not setting critical thinking skills as an educational goal? I'm truly going to pause now and give you a minute to think about that and write. So with that context, both the ideas that I've presented and what you've written down for yourself, we'll welcome Carolyn Maher to share research that can help us better unpack the conditions under which critical thinking takes place.
Thank you for that lovely introduction, Rebecca. First of all, I'd like to thank the Smithsonian folks who invited me to give this talk, Matt Schneps and Stephanie, and all the help that Nancy has given to make this happen. And at the same time, I'd like to take this opportunity to thank the many, many colleagues, former students, present students of mine, without whom this work would never have occurred. To do such intense work and follow a group for so long takes lots and lots of help. And it would just take probably a great deal of time to acknowledge so many folks. But I'm happy to tell you about this study. It's been the love of my life. And if I can get the PowerPoint to go. I'd like to give you some background in terms of how the study came about and how we got where we were. Somehow the talk was tested when I went out, and I'm not able to end it. Let's see. Well, you're getting a quick view of all the things you can see. But it will not, for some reason. Okay, here we'll go. We'll start from the beginning.
Press 1 and turn.
No, it's somehow not the same talk. Yeah, I did. It's not going to the second. I did, but let's try this. Okay, thank you. Okay, so you have to situate yourself in the study. A lot of you who are, I see many young faces here, you think about what's going on now as a lot of changes in school, more thoughtful curriculum, more active learning on the parts of students. But you have to know this study started before that reform. You have to think something like 24 years ago, where a principal in a school district, working class, with a population of parents who had low expectations academically for their students, maybe high expectations for them in athletics, but not certainly academically, believed that the students could do lots more than was expected of them and could achieve more advancement in many areas, but mathematics certainly is one of them. And he invited us, a few of us, he invited me to come and study the situation in this community, and studying of it resulted in a professional development program. Now imagine, we studied a program where mathematics was taught at most, if it were taught every day, a half hour, and the mathematics was really skills, memorizing, practicing, speed, fast. There was only one teacher in the entire K-8 district that used manipulatives, but the children didn't touch them. The teacher showed the children certain kinds of mathematical ideas, how they might be modeled with them. So we formed a partnership to have a professional development program that lasted a few years. And out of it came this sort of agreement that we would study the effect of this by randomly picking a group of students and following them to see how we could build on this professional development and continue it, because you see the professional development continues as we would work with children in the school. So you need to really also put in place that we were not there to teach the students. This was a research study. We had no particular goals that they had to learn X or Y or Z. We were really interested in studying how mathematical ideas developed in children under certain conditions. And the conditions involved collaboration with students, giving them sufficient time to work on problems and tasks. When I say sufficient time, I mean days, weeks, months if needed, and opportunities to revisit ideas over time. So what did that look like in terms of the time and with respect to the questions that we were asking ourselves? When the children were in the first, second, and third grade, we visited their classrooms about 6 times a year for 3 days each time. And we negotiated with the school district that we would have lengthened periods. We wouldn't have half-hour classes. We would have 2 one-hour-and-a-half class and a 45-minute class. And that went on for 3 years. From grades 4 through 8, we were in there 4 times a year with about the same allocation of time. Now, if you do the arithmetic and see how much time is allocated to teaching mathematics in schools today, 188 school days about, and now classes are 45 minutes, sometimes they're an hour, sometimes they're an hour and a half, you need to put in context the amount of time we were in the classroom and try to think about that was relatively little time over the years. When the children went to high school, we worked with them after school on a voluntary basis. And we went in for longer periods. We were there about 3-hour periods when we came in for a day or two, about 4 times a year. So we were interested in how mathematical ideas developed. Initially, that was our interest, or based on the definition Rebecca gave us, how do they learn to think critically? We could have asked that question years ago. I think it's an appropriate question. We were interested in seeing how they reasoned. And because the emergence of forms of reasoning just jumped at us early in the study, our research question shifted to study the forms of reasoning. And we're going to be talking a little bit about forms of reasoning today. We're going to be looking at examples of forms of reasoning. So I said it wasn't a teaching experiment. The question is, what did we do? Well, first of all, we dealt with areas of mathematics that children would not have been studying in school yet. If it came later in the curriculum, so that we wouldn't have the problem of the teachers maybe showing them how to do something, or explaining, or giving a very different kind of experience. We were interested in coming up with what I'm going to call tasks that were connected in strands by content that they could work on together, and we encouraged that they try to make sense of the mathematics that was really within the task, the structure of the task. So we invited them to explain their ideas and to justify them and to be convinced of them and to convince others of the logic of their ideas. We encouraged that they share, that they work together, that they collaborate. And our encouragement was really what we did. But we also observed what they did. We videotaped what we did with sometimes 3, 4 cameras. And we studied our videos. And on the basis of what we learned, we designed new tasks or extensions of tasks. And these new tasks formed the strands. What did the students do? Well, they worked together on these strands of tasks. And they were asked to provide convincing arguments. So let's look a little bit about our task designs. Our task designs differed from the kinds of tasks one often sees in materials children use in schools, in that we did not build from simple ideas to more complex ideas. We were interested in how ideas developed. So our tasks were complex, and out of the complex, we wanted to see how they dealt with the simple. You know, it's like that last problem that the teacher never gets to in your book, that the teacher skips in the problem-solving section. That's where we started, if that helps you. What we were interested in observing how students represented their ideas, what kinds of representations, what kind of notations, and how these were changed and extended. And we were interested in whether or not they generalized and in what way they generalized. I'm going to talk a little bit about all of these areas as we move on. So let's look at an example. Let's take an example from grade 2. We'll start with grade 2. This is called the shirts and pants problem. It's a simple counting problem. And Stephen has a white shirt, a blue shirt, and a yellow shirt. He has a pair of blue jeans and a pair of white jeans. How many different outfits can he make? Okay? Now, if we had time, I'd be really interested in seeing how you think about the problem, how you represent it, what images it evokes for you, and what images you think it might evoke for children or adults at different ages. So that would be one problem. Another problem, which has really given us lots of mileage, has to do with building towers. And I'm sure you've seen these little materials. They're called Unifix cubes. You can build towers with them. You can stack them. You can make them certain heights. That would be a four tall tower. And we would have them build towers selecting from different colors, maybe 2 colors, 3 colors, and of certain heights. Okay, so you could imagine everyone can build a tower. Children can select and they could make new towers, and they could look at what they make, and they could see, did I make them all? Am I missing any? And in trying to figure that out, they start to organize them particular ways. And certain kinds of heuristics come out of their actual working on the problem. So they could make drawings, they could actually make a physical model, or they could describe what they're doing in words. So that would be another example of a problem that we would give to young children. We see this problem a lot in textbooks today, so that's encouraging. But we ask children to do another kind of counting problem where they're asked to see how many pizzas can be ordered when you can select of so many toppings. Okay, so that's sort of a classic problem. Now, interestingly, about this problem, a 4-topping pizza problem is what we started with. The children in our study actually decided to solve the problem of pizza with halves. In other words, their experience in the world is that you really could just have half your pizza with one topping and the half of another, and so that's a different problem, isn't it? It's a little bit more complex. Well, I'm going to show you a little video in a little bit, so remember this problem of the pizza with halves. I'm going to show you this problem, and you're going to see one of the children's solutions, Encore. And you're going to see in this video that's going to come up in a little while how Matt, another one of the children, builds on Encore's idea to solve even a harder problem. Now, think about this problem. I don't think it's trivial for the folks in this audience necessarily, the 4-topping pizzas with halves. But you're going to see a video of these little 5th graders solving this problem. And what's very interesting is the very standard pizza problem that occurs in those textbooks today, the better textbooks, you know, the ones that have more thought in them. You'll see that this became a special case, and students solved it in about 5 minutes, working on the harder problem. So I want you to get the notion of complex, working with complex, and see how the simple comes out of the complex. That was very important in our ideas. The problems got more sophisticated. As the children were older, they worked with problems like this, more sophisticated counting problems. Have you seen this problem, the World Series problem? Some of you have seen this problem, I'm sure. In the World Series, 2 teams play each other. There's certain rules for, when you win a series. And this is a probability problem that's heavily based on counting. And it's the counting schemes that children built over the years that enable them to do really an elegant solution of this problem. So you're getting the idea of what I mean by a strand. Another follow-up problem, this is another standard classic problem. Have you heard of taxicab geometry? Those of you who live in cities, you know how cities have grids, and you look at, you're going from one street to another, and how many different ways can you get to one point to the next. That's really another counting problem. And this is a counting problem that also was in our strand of problems. The taxi cab driver is given a particular territory. You can see the taxi stand. All trips originate at this stand, and so on and so forth. What's very interesting in this problem, when we gave it to the children, they were now in high school to solve, they solved this problem, but they also solved the general problem, and we didn't ask them to do that. And we asked them, why did you solve the general problem? We only asked you to solve this problem. And they said, well, we know you would eventually have asked us to do it. So there's something about habits of thought, right? There's something about things that happen naturally. This is what we want, isn't it? If we ask them to do it, that necessarily doesn't happen. So keep that problem in mind. I'm going to show you a clip of it later of the students working on it. We had other strands. We have strands of early algebra. And actually some of really those videotapes, even though they were from a while ago, are now the subject of 3 doctoral dissertations that are being finished this year. So you're going to hear more about the algebra strand. And we had some beginning calculus, early calculus, and to give you an idea of the catwalk problem, some of you may recognize this from the problem from which this was derived about the horses. Do you remember this one? So there are photographs showing a cat first walking and then running. The interval between successive frames is given in so many fraction of a seconds, and they're shown a photograph and they're asked how fast is the cat moving on particular frames. If you're interested in knowing more about this, you ought to look at the Private Universe Project, which is the sixth CD or sixth tape that goes with it, which has wonderful video in it. And there's also a reference on the handout you received about this particular problem. So imagine, problem open-ended. How fast is the cat moving at a particular frame? Okay? And so this is another example of an open-ended task. I'm going to try to put this talk in terms of some kind of a timeline here. If you kind of see, we started working with the children in grade 1. We really just sort of did some problem solving, and we observed them mostly in grade 1. And grade 2, our open-ended problems were introduced. I'm going to show you what's in red on this screen. I'm going to show you some of the early building of towers. I'm going to show you a little piece of a clip of a video that's also on the Private Universe Project tape that you should really watch the longer one, or maybe even the full one if you'd like someday. I'm going to show you some of the children working on the pizza problem. I'm going to show you how they took these ideas later to work and developed some more sophisticated ideas, and a little bit of the taxi cab and some of the interviews we've had with the students when they were in high school and then when they were in college. So that's sort of what I'm hoping to accomplish given time. So let's move back a little bit. I want to go back to some of the things that Rebecca said earlier that I think relate here. You know, critical thinking. I didn't frame this study in terms of critical thinking, but it's really kind of interesting now to try to do that. So as I've thought about some of the things that Rebecca has written and what she's introduced to us, and I thought from our perspective, these children, the critical thinker would be one who was open to investigating new situations, comfortable in building new ideas, involved in interpreting, considering, and evaluating the ideas of others, not just their own, but of others, persistent in a quest for sense-making, and committed to seeking justifications. It has to make sense, and I should be able to justify my ideas. I should be able to come up with a convincing argument. And so this notion of arguing, I don't mean fighting, I mean arguing is healthy. Arguing because you're really presenting different perspectives and ideas. The importance of arguing. So in the early years, I think about critical thinking in the beginning as establishing our conditions, introduction to open-ended problem solving, collaboration and sense-making. And we saw that already as early as the second and third grade, that children were developing strategies in a natural way. They were not taught to use any particular strategies. They were not shown strategies. Out of their problem solving, they were guessing and checking. They were looking for patterns. They were controlling for variables. They were making representations like their own kinds of tree diagrams, maybe not the kinds you see in books. We saw those too. They were inventing notations. And by grade 4, already in grade 4, forms of reasoning very solidly were emerging. They were arguing by cases. They were arguing by contradiction. They were using inductive reasoning. They were providing recursive arguments. And they were using arguments of upper and lower bounds. In grade 4. We also have found this in grade 3 and other places. So, an example. Remember the shirts and pants, the outfits? Shirts 3 colors, pants 2 colors. How many outfits can you make? So we have Dana, for example, producing this solution. She has connected sort of a tree, and she has enumerated 5. And if you look carefully, the 5 she's listed are not the same ones as the ones she's connected. And she didn't connect, if you notice, the shirt, the yellow shirt with the white pants. And she deliberately didn't, because she made very clear on the video that that doesn't make an outfit because they don't match. And so if she were given a test, it would have been incorrect. But did she have a scheme? She sure did. And it didn't matter that she said 5, and we had to go home thinking it was 5. Now, her partner, Stephanie, had a very different representation. She, too, came up with 5, but if you look very carefully, a different 5. And if you study the video, you'll see she really did come up with 6. But she was very happy to go home thinking there was 5. Michael, on the other hand, invented his own third pair of trousers because for him, the solution, you don't have an outfit unless you have exactly the same color shirt and pant. And that was Michael's second grade solution. And then we have Jeffrey, who enumerated them all, got 7, but somehow put pants with pants, which accounted for his 7th grade solution. Now, I think it's really important to think about, we let them go home with the wrong answer. The children went home with the wrong answer. We went back about 4 or 5 months later. They're now 3rd graders. Whoops. I'll go back. What happened then? Well, Dana immediately, when she was given the problem again, produced 6, and she didn't worry about matching shirts and pants. And she represented her scheme correctly, accurately, and when she was asked what she did earlier, she said, I got 6. This is what she remembered. She remembered the reasoning. The answer didn't matter so much to her. What's particularly interested is Stephanie. Because if you notice, Stephanie didn't have a tree representation, but she did this time, which suggests learning from Dana. And not only does she have it, if you notice those little numbers across, she also had developed a scheme of keeping track. She kept track of the outfits. You see, she crossed out the numbers. So that's another scheme that Stephanie developed. Now, we talked about the towers problem. Remember, how many towers can you build selecting from 2 colors? When the children were in the 3rd grade, these are the kinds of ways they represented their towers. Notice the patterns? Now, this doesn't give you an exhaustive set to account for all possible towers, but you can see the early representations taking hold here. You can see the patterns. You can see that they invent groups. And they can't say they found them all. We were in a class of another school doing this task with young children, and they were also 3rd graders, and we asked them, okay, you think you have them all, but are you sure? And they said, well, you never can be sure. So we said, you never can be sure? Then one little boy says, well, maybe if you ask God. So there are differences, as you can see, in ages. Now, I'm going to show you a video of 4 children working on this problem as 4th graders, but you're not going to see necessarily what they're writing. Early, if you look at these, you can see there's a little bit of a pattern, but it's not really a pattern. They have them all. It's not really organized really carefully as a pattern, but you can see a little bit of all the reds, all the blues. Then you have one with a red, and then you follow with 2 with a red, and then you see what I'm saying? It's really not a really organization. Now, later in that same session, the organization gets to be a little bit more in terms of groupings, but it's not quite there. But you'll see by the time 4th grade, things change. And in 5th grade, they even change some more. When the children were in grade 3, they were pretty much able to produce 16 towers 4 tall, selecting from 2 colors. They weren't sure if they had them all. They were pretty convinced, but they weren't sure. Now, the children had 16 towers in front of them, 4 tall. And they were asked by a researcher, okay, you have 16 in front of you. You think you have them all. You're not sure. I don't want you to do it, but I want you to think about it. Suppose you were building 3 tall. Would you have the same number? Would you have fewer? Would you have more? Now, how many of you think they said the same? How many of you think they said fewer? How many of you think they said more? You don't count, Marjorie. They said more. and they were asked, why more? Well, think about it. See, we think the way we think, we have to think the way children think. And I'm going to show you a clip, but I want you to follow that clip. Well, if you're making them 3 tall and you have the 4 tall in front of you, you have to remove one of these blocks from every tower. Now, how many cubes have you removed? 16. So, I have 16 more cubes. I can build more towers. Okay? Let's look at the clip.
You have that one right there. Okay. Eliminate it. I know when I got it first. You have a mix. Yeah. It's less. It's only 8. Well, because once you take these apart, okay, once you take the parts apart, you start to see that they match because one taken off could mean a whole different.
First of all, what do you think you learned from what you did?
Well, we learned that, with the unifix cubes, we learned that even though there might be less, you might think that there'll be more because there's less blocks, so there's more combinations you can make. There's less because once you take one block off,
Did you do that for me?
say you have red, 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 and you have red, 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 blue. Mm-hmm. Once you take one red away and one blue away, they're the same.
Oh, you're right. Okay. All right.
So it was to say, now test your idea. You think there are going to be more? Do it. And then they find the reversibility. And you see the reasoning develops. Because you haven't told them the answer, they had a chance to figure out if their answer was correct. They had to pursue it. They had to test it. I'm going to show you a little clip of a 4th grade, 4 children, which we call the Gang of 4 affectionately. I want to tell you a little bit how this little video came to be. It's one of my favorites, and if you've watched the Pup Math tapes, you've seen it already. But the children were working now, they're 4th graders. They've been building towers 5 tall. And they were asked to come up with a convincing argument. They found them all. And some of these children were even pursuing 6 tall. They were pursuing selecting from 3 colors. But at this point, they were interested in how others were thinking about the idea. And one of the children here, Millen, he doesn't talk too much here, but he was thinking of the problem differently. He was thinking of the problem building it inductively. And so the way he solved the problem, he started with his red and blue cube. And on top of the red, you could either put a red or you can put a blue. On top of the blue, you can either put a red or a blue. And on top of each of these, you could either put a red or a blue, red or a blue. This is how Millen was thinking about the problem. Okay? Were any of you thinking about the problem that way? It is another way to think about building the towers. On the other hand, the organization this way was the way some other children were thinking about it by cases. And there were some children who were also thinking about some of this recursively.
A pattern.
Because we liked it. It's easier.
It's easier to find out
than just going, ooh, there's a pattern.
because if you just keep on guessing like that, you're not sure if there's going to be more.
It's easier. Maybe like Shelley and Millen's pattern was to go put this in a different category.
I know their pattern.
Okay, but what I'm saying is it's just easier to work with the pattern than to say, oh, here's another one. Let's see, that looks good.
Because you might have a duplicate, and then you may not know.
It's harder to check. It's harder to check just having them like come up from out of the blue.
going like this and getting two.
How do you know there's different things in the pattern?
And you can't make any more from this one, so you go on to the next one. All right, and
How do
these
you know you can't make any more from that?
because there's not any more colors.
Okay,
It's
start
great.
here.
Yeah,
Sorry.
sure.
Start here.
Here.
Okay, you have the three together. The one blue, right? You have the one blue. How could I build another one blue?
You can't.
All right, so I've convinced you that there's no more one blue. All right.
But if you didn't have that pattern, it would be harder to convince you.
Okay, so I convinced you that there's no more one blue.
Yeah.
All right, now we
You
move
have
on.
to go to two blue.
Two blue. Here's one, right? Two blue. We have one blue, blue, red. Then we have red, blue, blue. But how am I supposed to make another one?
Blue, red, blue.
No, this is together. No one gave me that same
She
argument.
means
But the
together.
thing is that doesn't
But
matter.
I
if
don't
they're
know.
She means stuck together.
Stuck together. That means, like, okay,
I know.
Okay?
And then
So
you
can
would
I
have
make any
to-
more of that kind?
Then you
All
would
right.
have to move to three, which you
All
can
right,
only make
then
one.
yeah, you can only make one, and then you can make the three without blue, which is three red.
And then you can make two split apart.
Two split apart, which you can only make one of, and then you can find that you can find the opposites right in the same group.
Okay.
All right, so I've convinced you that there's only 8.
Yeah.
So the notion of convincing, the notion of trying to make your argument explicit emerged as 9-year-olds, really, quite early. And I think that's an important finding from our study. And having noticed that, as we continued our work, we started to focus more on the forms of reasoning, which was not our initial goal, but it became a very important goal in our study even to today. The kinds of reasoning and the forms of reasoning, particularly the forms of reasoning that we identify as mathematical reasoning. So the extension in the middle grades were broadening the context, early algebra, probability, more challenging counting problems. They worked on the Tower of Hanoi. That's another PubMath video that you might want to take a look at, classic problem. And in the later grades, more on their formalizing and generalizing, more of their moving from their own personal notations that they invented to connecting it to standard notations that they are expected to use in school, and also justifications that were not problem-specific, that ones that could go across problems and that could lead to generalizations. So remember the pizza and tower problems that I told you about earlier, okay? Just remember building towers that are so high and selecting from cubes in so many colors. And the pizza with halves, for example, how many can you make if you have to choose from toppings and you're allowed to have half? We saw the Stephanie's reasoning where she was sort of hung up with her own organization in that she did, for instance, no red. She did exactly one red. This was her written work from that session, sort of her written work from that session. Then she did 2 reds stuck together, and then she had 3 reds, and then she had 2 reds separated. But you notice here, she has her reds stuck together, she has her 2 reds separated, and then she has all reds. In a natural way, when we gave her the same task a few months later, she produced the more elegant organization by cases. And I don't have time to go into it here, but she also produced elements of the inductive reasoning that came out of that session for her possibly for the first time. And what's important in that is that Stephanie, for example, was able to build this tower representation to solve the problem, the same problem that she organized by cases in the 5th grade. So you can see that some children preferred one way of reasoning early on, were introduced to the reasoning of others, had a chance to think about it, reflect upon it, and had an opportunity to show that also structure was also something they could connect to. And that was important to us in our research. I want to show you another little clip. It's fun to watch the children rather than listen to me talk. And this is a 5th grade session, and Ankur and Matt are working on the pizza problems. First, the pizza problem with halves. They're working with a group. and then the whole pizza problem. So I want you to pay attention also to how Matt builds on Encore's idea and how Matt attributes his idea to Encore. These children are incredibly honest. As we watch the videotape, if the idea came from someone else, they say, oh, I got this idea from Michael, or I heard this from Robert, or, I was listening to so-and-so. So that they're very honest about where the origin of their ideas came from and are accurate probably 98% of the time. They might not remember the person exactly well, but they still do the attribution, which is really very nice. So let's take a look at this, because this kind of thinking is another form of reasoning that we might call recursive reasoning.
I had a pen.
What was your pen?
I started with the first one and mixed it with the second one. So my first one was peppers and sausage. So I took peppers and slashed sausage. So I skipped I started with the first one again, skipped the second one, and took the third one, P/M. And then I put peppers and skipped the second and third, and I went with the fourth one, P/PE. And then I started with the S.
And so you were sure you were finished then. And then what did you do?
Then I started with the second one. I started with the S, the soy sausage, and mixed it with mushrooms. And then sausage and pepperoni. And then I went down to the next one, mushrooms and pepperoni.
Encore's idea of holding one topping constant and changing the others is a strategy that Matt noticed and will use again in the next problem.
We started with peppers and pepperoni and added.
Okay, you'd say peppers and pepperoni,
And then we added
and you added
sausage,
uh-huh,
peppers and pepperoni
uh-huh,
with mushrooms.
uh-huh.
And then we couldn't do any more with peppers and pepperoni.
Okay.
So then we figured out peppers, sausage, and mushrooms.
Peppers, sausage, and mushrooms. Yeah. Is that all?
No, and there was no more for peppers. We convinced there was no more for peppers.
That was all you could do with peppers, yeah.
There was only one thing you could do with pepperoni.
Which was?
Pepperoni, sausage, and mushrooms.
And then you were done?
And then we had the big one, the four-topping pizza, which was the pepperoni, the peppers, the sausage, and the mushrooms.
Yeah.
So you can see another kind of reasoning from this clip. And these early ideas in counting, I'm going to show you some examples of how they even built them further and made some very important connections. Now, just to put this again in a context and a setting, by the time they're in the 10th to the 12th grades, they are noticing the structural equivalence of many kinds of problems. And they're able to relate their early building and make these connections. And they were able to do this in a formal way, using standard notation and generalizing. And I'll show you also in some of the interviews in a few minutes how these ideas stayed with them, how they revisited, they could reconstruct, even though they hadn't looked at them. You think about if you're in college now and you haven't looked at things in a while, would you still be able to rebuild them? If it were just a formula that someone told you, you probably would get it mixed up. That's what we find. But if you built it once and really understood it, you can reconstruct it. That's our goal here. So I'm going to show you hopefully a little piece of this if I don't run out of time. So we have, you've seen Pascal's triangle? Have many of you seen this? Raise your hand if you've seen this. You see this? You can go on the web and search a lot about Pascal's triangle. I encourage you to do this. But if you look at those numbers there, you can see how the numbers on the lines that follow come from the lines before. Do you see a pattern there? How many of you see the pattern? You see the ones at the ends? You see the 1, 1 producing a 2? And you see the next line, 1, 3, 3, 1, etc.? Well, the students were aware of this triangle, and the question they were asked is, how does the triangle grow? How do you explain this pattern? How do you explain this pattern? And one of the explanations came about by looking at the towers. You see the towers there? If you see under the number 1 on that fourth line with the numbers 1, 3, 3, and 1, you can see one of those towers that's all white, right? But you can see 3 towers that have one of the dark colors. If you're thinking of red, 3 reds. If you're thinking of blue, 1 blue. And if you look to the next line, you can see how you can get the towers on the next line from the line before. Because you have a choice on the top of the tower, just like Stephanie told you earlier, you can take one off, you take a red or a blue off, now you can put a red or a blue on. You see, and you can count and you can generate your pattern. Well, that's something for you to think about. The children discover this. And what's really interesting is they also discover this and they're working on the pizza problem, the same relationship, but they did it with zeros and ones and the invention of binary numbers. That's something else for you to think about. It was their invention. Now, this is pretty interesting because they really did use binary numbers to count. But there's another little video you should look at of a 4th grader who did this and discovered this relationship. They weren't binary numbers, but it was zeros and ones. And that's also in the pub math tapes. You might want to take a look at Brandon and the pizza problem. Now, when I talked about formal notation, this is the stuff that scares most folks. You like this notation? See, this is the rule that when Matt visited us at Rutgers, you remember that, Matt? That night, I call it the night session, the children produced this rule, which is the generalization of the generation of the towers and pizzas. And the use of that notation is really nice. It came from another representation where they now understood to represent the entries in this triangle using this particular counting combination selection scheme. Some of you must have seen this in some of your schoolwork through, right? You've seen this combination notation, right? Do you remember this? And so that led to this general expression, which they produced on the blackboard when Matt was visiting us on a Thursday evening where they volunteered their time. It was a very special Thursday evening because they had a prom the next night and they were coming in with their tuxedos or whatever and still stayed there to work on this problem. And so if you looked at the clock, which we did film, we thought that was silly because it said 8:30 at night because people could have thought it was 8:30 in the morning. But they were there 8:30 at night working and volunteering to work on this problem. So what do you call that? Persistence, perseverance? Is that an important attribute in critical thinkers, Rebecca? So let's look at a little clip of their doing it so we can bring you back and you back to Matt to that night. Well, I want you to show me how the addition rule works in general.
And choose x plus and choose x plus 1
equals that.
plus 1 equals that right there. Then, well, that's because this would be gaining an x and going into the x plus 1,
Yeah.
and this would be losing an x.
No, not getting.
That would be staying the same, and is the x plus 1
And the top number's gonna change because
because you have more things. And why do it is because when you add another topping like onto it, this one, say toppings were 1 and 0. If it gets a topping, that's why it goes up to the x plus 1, and since it doesn't get anything, it'll stay the same. And then this one is staying the same, right? And that's why it's going there, like saying that's the 0.
Okay.
And going to there. Makes sense?
Yes.
So that would be the general addition rule. In this.
Do you recognize Jeff from the other video? He has a lot of different looks, Jeff, as you'll see as we look at this. Jeff also commented at the end of this when he produced the same formula using factorial notation, saying, could you imagine how intimidating this would be if we looked at a textbook and saw it? Remember this problem, the taxicab geometry? I want to show you a little clip of their working on this solution.
What we did is we took it We broke it down.
Yeah, we just went from point to point on the thing.
Like we even rules to say we started making a box like that. How many different ways can you get from this point to this point? You know, make it easier problem, like the basic math.
So we did, like up to this point, there's 2. Up to this point, there's 3, 4, 6, 3. So those are our numbers. Those are up to the points, like down a diagram. And what we got is Pascal triangle.
Yeah, we started, and then as we started, like it takes 2 to get to there, 3 to, to get there, as Romina just went through and did. And then as we started filling it out, we noticed that if you tilt it like that and throw 1s on the outside and a 1 on top, I mean, you're looking at Pascal's triangle. And so we stopped at this point because, I mean, making, like 30 plus different things like this, it just gets confusing, And so Brian was doing, some of us were drawing out all the ways. Brian had another method of finding out the ways to do it, and we just brought it all together, and then that's kind of what we're looking at right now.
Okay, so this is bringing them back to think about the problem, and they're still making the connections over many years. And I think that's sort of interesting. So what did they think about all of this as we interviewed them? We brought them back while they were in college. They joined some of our doctoral seminars, and they talked about their experience. I'm going to show you a few excerpts about what their view was. This is Brian.
Courses. I would make everyone hands-on because no kids get tired sitting there. But when you're up doing things, time flies and you have fun and you learn, which you retain more of that. Just think about, I remember when we were working with the wheel. I remember I was sitting in class listening to the teacher.
And this is Jeff talking to a group of graduate students.
We know it's right because we did this, and that's why it's right. We came to an answer ourselves, and we worked it out, and we knew it was right because we explored all the possibilities and we proved it ourselves. And when we were building in that type of way, we're just building on our own work. And by the time you come to the end of that, I mean that's solid. If you work through the whole thing yourself and each proof is your own answer, and because it's true because you did it and it's your own reason why it's true, then I mean that's solid. That's a solid proof, and then we know what we were doing. We didn't prove it because of what someone else said. We were proving it because of what we had done when we were working on the problem.
Do you know what he majored in? English. Okay, I don't have time to go through all of these, but...
When I say kids running, I mean kids like discovering new things and on their own. It definitely it's a lot different than just copying down. Like you figure whoever came up with these triangles, Pascal, he was doing it for the first time, so he completely understood not everybody how that triangle relates to things. And I guess if you discover it for for the first time yourself, then you kind of get the same understanding as he did. That's just with that one example. And with anything else, like if you go through it and it's like learning these things for the first time, even though they were done in the 1500s, I don't even know. But it's you definitely get a different understanding if you sort of run the class yourself. If the teacher just starts blurting out information, you just get the surface. You don't get what's underneath.
Okay, and I have one little short one to hear from Romina.
It's more than just numbers to me. It's like almost like you have to go deeper. You have to if you understand something from the beginning, you're going to always understand. You can't forget something like that.
So the notion of what you remember, and you have to look deeper, and what you can remember and forget. You might want to see where they are now. I always like the where are they now, because that keeps changing. You can see what their majors are, what they studied in undergraduate school, and sort of what they're doing now. It's really an interesting collection of interests we have. They didn't all study math. I guess we can count Robert for being the one to study math. He's going on in statistics and actuary work, and Michael, computer science, and we have some economics for the women, young women, working in consulting firms. But you see a range of professions here. And I think the text is still being written about where they're going. But they are continuing on an interesting journey, and it'll be fun to follow them over the years. So you can think about that. That's on the website. But what do they say? I mean, if you look at Robert, for example, who did major in math, he talked about he learned from this experience, which they tend to call Rutgers math, how to tackle a problem that's foreign, how to relate one problem to another. Also, we also hear from Angela, the why was so important, okay? When you understand the concept, you always have the resources to find the solution. Learning to understand is what they talk about. Not where I don't remember the uses of particular theories and forms, I'm sure if I worked through it, I could reteach myself. That notion of I could reconstruct it. Ways of thinking, okay? Brian, who's studied criminal justice, says the ways of thinking are what's important. Matt talks about, he's a project manager, lessons of teamwork and communication. He says now they're very important in the work he does, and also having to lead teams himself and have people work together. Communicating and explaining your ideas, important. I don't see these as curriculum in school. The ability to listen, the ability to communicate your point of view effectively. Teamwork, communication. This is how he goes about his everyday problem solving. Okay? Angela talks about critically thinking. She's also doing some teaching, and she says, and also Amy Lynn, who's doing some teaching as a doctoral student. They say that I don't let my students, I don't lecture at them, I make them do the work. So there's something that looks as if it's carrying through, not about memorizing and plugging in numbers. Critical thinking, how to think for themselves. She thinks it's important for her own students. So to summarize, generally, what are some of the important findings in this study? Well, we have found that children can do meaningful and challenging math at an earlier age than generally expected. And I suspect if we even go earlier, we're going to find more amazing things. Those of you who have young children know this. They naturally try to make sense of their ideas and to provide arguments that are convincing to themselves and others. They do this in a natural way. And ideas that are built with meaning are durable and that they can be reconstructed, extended, and refined. So critical thinking, I believe, is possible at all ages, given opportunities to be engaged in thoughtful problem-solving activities. And as you can see, the students emphasize the importance of being personally engaged in the learning. Revisiting topics gives them the opportunity to reflect, refine, and extend their ideas. I just want to show you very briefly, we have an informal math project we're completing from a National Science Foundation research, beginning with urban, minority, poor kids, starting in 6th grade. That's tough, you know that. 6th grade, after school. And this work comes from a doctoral dissertation recently completed by Maher, where only in 5 sessions where I worked with these students doing these open-ended problem solvings to help them learn how to work together. You can see how they learned to co-construct together. They didn't start out that way. And the different forms of reasoning that evolved, and if you look at that chart very carefully, you can see that those forms of reasoning were not just one student. All students were contributing to those forms of reasoning. That's optimistic. We also found that these data have not yet been published, but they did significantly better than their control group in the standardized tests, which we're asked to always look at for the group of students that were actually led by teacher interns. So for all of us, we have opportunities in informal math learning. I really think of this study as informal math learning. This was not part of the curriculum of school. And it was after school later. And the opportunities are great for students and they're great for teachers. And I think the challenge for all of us, you in this really wonderful environment of the museum world, can provide incredible opportunities for this excitement to learn and enrichment with strands of tasks and ideas that children could revisit and look at with different lenses over the years. And I think that a lot of this has to be done after school. Maybe if it's done after school, those models will eventually be taken into school. We can only hope. So this was a reunion. Thank you very much.
it's open there. I can do it. Okay, now. Thank you. Thanks, Carolyn. Every time I talk to Carolyn about her work, I feel like there's so much to unpack in terms of overlaps between what we do in museums and the kinds of things she's exploring. But what I want to do now has a few parts. The Guggenheim has also been conducting research into critical thinking and problem solving. So while I was initially invited here to respond specifically to Carolyn's research and to contextualize that in terms of its implications for museum educators, I also do want to talk about the research that the Guggenheim is going to be doing and has already done. So in order to do that, I want to start by describing the Learning Through Art program at the Guggenheim, also called LTA, which is the context for our research. It's the program we've been studying. And then share a recently completed study teaching literacy through art, which really looked at how the program teaches literacy and critical thinking skills. And then share a study that we're embarking upon right now, which is the art of problem solving, and is looking at the impact of our program on problem solving skills. And then finally, I want to share some thoughts regarding the implications of all of these studies for museums and critical thinking skills. And I'm going to keep an eye on my watch so we have time for questions at the end. So Learning Through Art, or LTA, is a 37-year-old program of the Guggenheim Museum. We send teaching artists into New York City public elementary schools where they collaborate with classroom teachers to design and lead projects that support the school curriculum. There's extensive collaborative planning time before the project begins, and the residency itself includes 20 sessions in the classroom with the teaching artist and 3 visits to the Guggenheim. Each classroom session includes both looking at and making art. We have a few guiding principles that help us shape the program. The first is art as exploration. We envision the program as a triangle that brings together art, curriculum, and students' own lives and ideas, and a strong art project lies at the center of these 3 points. And I think that's not unrelated to what Carolyn was talking about in terms of the students making their own meaning of things. The second principle is collaboration. The project depends not only on what the teaching artists do when they're in the classroom, but on what the teachers do. We've slowly built up our planning time and our resources so that we can help teachers plan their related curriculum and map the art and non-art curricula together. And the third principle is continuous improvement. We see the program as constantly evolving, and whenever we implement or use an evaluation strategy, we think not only about what data we want to collect, but how it will inform program change. How are we actually going to take that data and make changes based on it? We try to encourage the same way of thinking in the teaching artists when they reflect on their own work in the classroom, and also on the students as they look at their own work and reflect on their own artwork. So just a couple examples of projects, 2 third-grade projects. This project, students explored the question, how does geography impact our lives? First, they mapped their own neighborhoods, and they studied and played around with changing the map of New York City, and then later China. In New York City, the curriculum is mapping skills and then studying communities around the world. They then looked at their own school playground and at artists who create geographical interventions, such as Richard Serra and Robert Smithson, and they designed and built site-specific geographical interventions for their playground and photographed them. And that, by the way, was on view in the Guggenheim Museum, not in their playground. Here, students were looking at the rainforest, and they were wondering about how living creatures adapt to their environment. So this was a very tall project. It's probably actually projecting at about the size that it is. In groups, they studied the characteristics of plants in different layers of the rainforest and how they're adapted to that layer, and then created their own imaginary plants adapted to the layer of the rainforest. And this very large group mural was the final step in the project, and the imaginary plants are prints in the rainforest that's paint and drawn. So this was the program that we're studying. In our first study was teaching literacy through art. We had applied to the United States Department of Education's Art in Education Model Development and Dissemination Program to fund this study in 2003, and I wanted to note that we felt that we'd be competitive for this grant because we had begun to work with an evaluator, Randy Corner and Associates, to develop a program rubric that helped us to understand what our program would look like if our goals were being reached, which was a well worth it investment of time and money. Small time, small money. Research, big time, big money. So our research questions were, does learning through art teach students how to be better critical thinkers? And does this transfer? Does this help them become better readers? If they can think critically in front of an artwork, can they also think critically when faced with a text? So we again worked with Randy Corner and Associates, who conducted the research that I'm about to describe. We recruited 4 partner schools, 2 of which we had relationships with and 2 of which were new, and we divided them into 3 groups. We had treatment group A, which was students and schools who received the program. And then we had treatment group B, because we weren't convinced we would see an impact from treatment group A. We weren't convinced that the Learning Through Art program would actually result in students who could better comprehend a text than other students. School has so many components. This was something that they did for 90 minutes a week for 20 weeks. So for treatment group B, we gave professional development to the teachers. We taught them how to lead inquiries with art in their classroom, and we helped them write their own inquiries, and we asked them to make the transfer explicit. So, for example, if they had been studying compare and contrast with a work of art, and then they would look at 2 poems and say, remember how we looked at art last week in the classroom and we compared these 2 paintings? Well, today we're going to look at these 2 poems and use the same skills to compare and contrast them. And we were very influenced by a book by David Perkins, The Intelligent Eye, where he posits that in order to see transfer, you will need to have both as many interventions as possible, and you'll also need to make that transfer explicit. And poor treatment group C is our control group, and they did not get anything. The school got some things, the kids did not. We had a number of research instruments, both to measure teacher impact and to measure student impact, and the most important of them were rubric-scored student interviews. So we had worked with a literacy team for the first year after we received the grant funding and before we began the research to develop a list of 6 critical thinking skills that we thought that our program might teach. And we used the rubric based on these skills to score critical thinking and literacy skills demonstrated when students did 2 tasks. First, they looked at The Artist and His Mother by Arshile Gorky from the Whitney's collection. We specifically chose a work that we expected that they wouldn't have seen, and we told teachers and teaching artists not to have shown this to kids. And second, when looking at an excerpt from a young adult novel, Kira Kira by Cynthia Karahoda. And it was interesting how hard it was to find a text in which kids, 3rd grade students, could demonstrate critical thinking skills. Our literacy team first suggested a book of poems by Jean Little, which are fabulous poems, but they're sort of one answer. There's not a lot of various interpretations to be made. So what we found was that when looking at the artwork, students in our program demonstrated, they did better at 5 of the 6 skills: extended focus, hypothesizing, giving evidence, understanding that there are multiple interpretations, and schema building, which is the literacy term for connecting to prior knowledge. When looking at the text, they also did better on 5, a different 5. Extended focus, thorough description, hypothesizing, giving evidence, and multiple interpretations. So this is all of the students in our program, whether they were in treatment group A or B, no matter what professional development their teachers had, they did better in all of these literacy skills, both looking at the artwork and reading the text, than the control group students. We have a number of sort of theories about why which show up do, but the findings can be found on our website, learningthroughart.org. So now I wanted to turn to the art of problem solving, which is the research that we're embarking on now. And I just wanted to also share that Carolyn and I had an interesting conversation I also had with a number of the other organizers about this event, about the difference between critical thinking and problem solving. And my father last night said they're both just jargon. And I think that's kind of the point. I think we haven't defined either. So they sort of both mean the same thing, but to me they also sort of mean different things. And it's very interesting to try to unpack what we mean by critical thinking and what we mean by problem solving. We've been working with another advisory team, this time to think about the question, does learning through art teach students how to become better problem solvers? We're going to look at 5th grade students this time, because with 3rd grade students, we did not see that an art program increased interest in school or art in general. 3rd graders like school and they like art. So it'll be interesting to see what happens when you get to 5th grade and they're not so crazy about school. And so we're working with these advisors right now. Our actual research will start next year to think about what are problem-solving skills that our program could teach, and then to think about what are the teaching hallmarks that will lead to the cultivation of these skills. So the problem-solving skills that we've come up with so far are imagining. This was the most interesting one to me, that students can place themselves within the task and envision the problem beyond the assignment given. Experimentation, that they try different things. Resource recognition, that they sort of know what might work to help them solve their problem. Flexibility or persistence, that Carolyn was talking about. Students approach obstacles, accidents, etc. with tolerance. They don't get frustrated too easily. And connections of ends and aims, that students can keep in mind what they're trying to do as they make their choices. And the teaching hallmarks are really even more still in development, so I just wanted to show the thinking that is happening as we try to figure this out. But it has to do with recognizes, encourages, demonstrates, and shows examples of are sort of the ways in which teachers interact with students that we've identified. But thinking about multiple approaches, individual solutions, questioning, reflection and metacognition, creating a community of artists by focusing on process or ideas rather than personal criticism. If you're saying that so-and-so's ideas are wrong, not focusing on that student as being wrong, but that idea. Teaching art technique and materials usage, experimentation, scaffolding for individual students as well as the whole group. And all of our projects have an essential question that they're based around, so a question such as how does geography impact our lives, and revisiting that essential question over and over again, which again I think is somewhat similar to what Carolyn was talking about when she would have the kids come back to the same types of problem solving. So those are the 2 research studies that we've been working on. And our research won't be finished and available until school year 2009 to 10, so stay tuned for that second one. But now I want to consider the implications of Carolyn's work and the Guggenheim's research. And both of those were school-based programs. Learning Through Art is a museum program. It is run by the Guggenheim Museum, but it really is a school-based program. We meet with the students 20 times. It's different than a school tour program. So the question is, what implication do these studies have for what happens in the galleries? So first, I was madly working on this yesterday on the airplane, comparing Carolyn's study to ours, and it was interesting to try to put what she listed as critical thinking skills next to what we had listed. And I think there's a lot of overlap. I think hypothesizing and giving evidence is similar to persistent in a quest for sense-making, committed to seeking justifications, that multiple interpretations has to do with involved in interpreting, considering, and evaluating the ideas of others. And schema building is the same thing as, or similar to, open to investigating new situations and comfortable in building new ideas. It was interesting to me to note that what Carolyn didn't have on her list, and what I think is really important to museums in general, is that looking carefully, thorough description, extended focus, being able to look carefully for an extended amount of time at an object and to really know what you're looking at, think carefully about what you're looking at. I still don't know whether that's an important part of critical thinking or just an important part of critical thinking for museums. Sorry, I'm finding where I am in my notes. So the first question that I had based on these research projects is, what types of interventions teach critical thinking skills? And I have to say, as I go through these, it was really difficult to find images online that related to what I wanted to say. First of all, I noticed that museum websites do not have a lot of pictures on them. We all might want to think about that, more pictures of people in the galleries. But I don't think we know what most of this looks like in the museum. We might know in the classroom, but we don't know in the museum. So what types of interventions teach critical thinking skills? The first idea that I wanted to put forth was don't share the answer. And Carolyn talked about this, and I think it's actually quite controversial. This notion that you could spend 90 minutes with a group of kids having them solve a problem and not let them know whether or not they came up with the right answer in the end. I had a conversation with Carolyn about this, and she pointed out to me that what would happen if she tells students the answer at the end of that is that's the end of the quest. Okay, I tried to figure it out. I may or may not have figured it out. You just told me the answer. That's the end. And I wanted to share an experience that I had with a zoo education program. And great program, they gave a group of educators replicas of skulls, and they asked them what they could figure out from the animals by looking at the skulls. And they were working in small groups, looking very carefully, trying to figure it out. And there were some really brilliant answers, but in the end, everybody wanted the zoo educator to tell them the correct answer. What animal did they have? And the zoo obliged, and then it was over. Oh yes, well I thought it was a mole, but it was a large rat. I thought it was an owl, but it was, something else. And after I spoke with Carolyn, I wondered what would have happened if they'd sent people home with a picture of the skull, and maybe discussed where they would go to find out what their animal was. And instead of closing the activity, sort of talked about where those sources of information came from. But I think another factor in the don't share the answer issue is considering what types of questions we're asking. And Carolyn talked a lot in her talk about open-ended questioning. And I think I need to learn a lot about what people mean by open-ended questioning, because I think all of us mean different things by it. In an art museum, we typically mean asking a question that there is no correct answer to. Whereas in a science museum, and I think in math education, you might mean asking a question to which there is no one way of finding the answer, which I think is very different, and I don't know whether there should be different terms attached to those. But I would argue that however you pose the question, whether there is an answer or not, a good question should be one that the educator and the students can explore together. And I do think that's easier in an art museum where there tend to not be correct answers, certainly with contemporary art, where everything is left up to the viewer. But back to the zoo, or you could refocus on the process, how people solve problems and come to the conclusions rather than thinking about what the conclusions are. So bringing that back to the zoo example, another thought I had was, what if they had made a list of all the ways the teachers tried to gather information about their skull and what their animal was, and then they had focused us on that list and taken us somewhere else with that list. So for example, the size of the eye holes, the shape of the back of the skull, the size of the brain cavity. And then they could have taken that somewhere to tell us something about the work of zoologists or paleontologists and how they go about their job. Then that would, in its turn, have opened up a new type of quest for us and left that open. And I just wanted to share, this is on the picture on the right, and the words on the bottom are from our website, learningthroughart.org, at which we sort of share for teachers how we conduct inquiry in the galleries. And even within Art Museum, I think how you talk about objects or how you ask questions about objects has some debate or many different ways of doing it. And what we do is to ask questions that are open-ended, meaning that the person who's asking them does not have an idea of what the answer is. And if they have a strong opinion about what they think the answer is, they should not be asking that question. And we offer information where it will further people's ability to address that question. And we articulated our strategy for inquiry very clearly while we were engaged in our research process and thinking very much about what the critical thinking skills we wanted to be teaching through doing this are. So it's interesting to sort of think about the different teaching techniques and what goals we had in mind when we formulated those teaching techniques. So the second idea I wanted to talk about was fostering argumentation in programs. And there are many different words for this, but Carolyn set the conditions for this by asking that students come up with a consensus, I believe, at their table. Is that correct? By the end? Oh, no, convincing argument. So, and in our study, a number of the skills that we looked at had to do with having, arguing, and responding to differences of opinion, understanding multiple interpretations, hypothesizing, and giving evidence. In the upcoming issue of the Journal of Museum Education, Mark Felton and Deanna Kuhn write that argumentation forces people to consider not just what they know, but how they know it, which they call the heart of critical thinking. So according to them, what critical thinking is when you state something you think to be true, actually thinking about how do you know that to be true. And they have some great anecdotes of people who aren't quite thinking critically in their article. And I should just add, by the way, that this issue is coming out in August. The Journal of Museum Education is on critical thinking. And if you're a member of MER, you will get it. If you're not a member of MER, you can either become a member of MER or you can purchase it directly from Left Coast Press if you wanted to read a series of 6 articles about critical thinking. I also wanted to add about argumentation that it's really hard to foster argumentation. I see this a lot in the galleries when I walk around and hear people leading inquiries about artworks. What I notice is that often people will say things and not be asked to back it up because it really feels like you're challenging kids or visitors. It really requires asking for evidence. And the third thing was about fostering argumentation in exhibitions, and this is something that Mark Felton and Deanna Kuhn talk about, that exhibitions could potentially that exhibitions could be presenting us with multiple voices instead of a single voice. But even when exhibitions, most of the ones that I've seen, do present us with multiple voices right now, there are multiple ways of looking at something and not voices in conflict with each other. But you could, curators are making choices about which of 2 opposing arguments or 3 opposing arguments often they agree with, and you could present all the different evidence and talk about why the curator has made certain decisions and even let people make up their own minds. The second question I think that comes up related to critical thinking is about how long interventions have to be. And this is really a difficult one for museums where we often see people for an hour or 90 minutes. Carolyn saw her students for 12 or 18 sessions a year, and at Learning Through Art we saw our students 20 times. We don't really know what the impact of a single tour is or a single visit is. I'm not sure that anybody's ever studied the impact specifically on critical thinking skills. But there are programs run by places like the National Gallery of Art and the Isabella Stewart Gardner Museum that have looked at the impact of their 5 or 6 visit programs on critical thinking skills and seen that they can have an impact. So if teaching critical thinking is an important goal for museums, how do we spend enough time teaching visitors to do this? And again, another thing from this upcoming issue of Journal of Museum Education, I wanted to bring up a factor that Ron Richart from Harvard's Project Zero mentioned, which is that even within the context of a single visit tour, time is something that you really need to attend to because thinking takes time. And if you spend 3 minutes in front of an object and then move on, there's not enough time to think. But most visitors, including teachers and their students, expect to see an entire exhibition when they come to a museum. And so somehow we need to find a way to shift those expectations so that we can encourage people in an hour-long visit to the museum to see 4 objects and think about them instead of 50 objects. So another idea that I wanted to propose that has to do with how many contact sessions you can have with students is offering multiple visit programs as the standard school tour unit. And I say this because so many museums, when I look on their websites, are claiming that their programs teach critical thinking skills or listing that as a goal of their programs. But when you look at their school tours, the thing that pops out is a single visit tour. There's no obvious multiple visit program offered. And here are pictures of the National Gallery of Art and the Isabella Stewart Gardner Museum, but they have specific partners for their multi-visit program. I don't think a school can just call up and say, oh yes, I'd like to be part of the school partnership program, or I'd like to be part of Art Around the Corner. It's an intense collaboration. But you could offer multi-visit programs that are essentially a series of 3 or 4 single-visit tours without a huge amount of adjusting of the kinds of interactions that you have in that with teachers. And then if you had consistent goals for teaching critical thinking, you would have, let's say, 4 context sessions with those students to try to teach those. I also wanted to put forth this idea of interinstitutional multiple visit programs, and I was specifically thinking about that in the context of the Smithsonian Institution, where you most likely have kids in a class who visit the National Gallery of Art, for example, once during the school year, but who visit all the museums on the mall a total of 4, 5, 6 times. And if the museums were able to collaborate and come up with a shared set of goals for one version of the school tour program, and people went to 5 institutions during the year, they'd essentially be participating in a multiple visit program that hopefully was fostering argumentation and in other ways helping to foster critical thinking skills. And lastly, I wanted to think about designing exhibitions to encourage extended looking. There's even contemporary art being made now about how people don't really look at art in museums or look at objects, how people look at an average of maybe 2 to 3 seconds at an artwork in a museum, and I think this is true with almost any object in a museum, perhaps with the exception of dinosaurs. And there's a lot of sort of blame on the age that we live in and the large amounts of information that come our way and short attention spans. But I have a theory that this is actually a situation that museums have set up all by themselves, in that we do have exhibitions with, you read a press release from the Guggenheim Museum, and it talks about the 300 objects in that exhibition. So you can't spend too much time in front of the single object. And I was very impressed with this image from the Museum of American Art here, where they've created a space in which you're encouraged to sit and contemplate. And it would be nice to see more of that if we want people to be thinking critically in museums. So that is the end of my thoughts on the implications of all these research studies. And now Carolyn and I wanted to take questions, if people have questions that we can answer, debate. Carolyn's going to come up here, I think. How do we get that off there, right? Be brave.
Be brave. But not this one, because I'm going to turn it on.
Should we ask questions of each other? Wait time.
Maybe you can repeat my question.
Oh, there's someone with a mic for you.
Thank you. I'm wondering about the empty box in that table you had comparing critical thinking in art and critical thinking in mathematics. Is that box empty? Can you talk about that some?
Yeah, go ahead. That's the observation box.
No, I really don't think it's empty at all. I mean, I think that's very fundamental to what children or adults or learners do. They have to pay attention. They have to observe. They have to pay attention to details. Now, it's not art. It's not looking, but they need to look. They need to look at each other's work. They need to look at what they build and what the models. I think that box is quite full. I think there's a parallel there. So I'm glad you asked that question. I mean, it's not something that I ever thought about documenting, but if you ask, I think it would be easy to do. Thank you, Matt. Do you want to comment on that?
No, no.
I didn't say it because
Yeah.
it never occurred to me.
Yeah, I mean, probably a lot of people don't think enough about just offering time to look. You notice this actually in meetings all the time, where someone will produce a list of notes and say, okay, let's talk about this, without giving people to go through and review the notes or something. So it's interesting to think about how that one drops off quickly, but it's, I guess, important to all fields.
Yeah, what I'm trying to say, one of the conditions is to give students sufficient time. There was one of my students, this was Janet Walter, did a study. The students were working on the placenta serous task. Do you remember that task? They were trying to see how the animal grew. This is the same group of students. And what she studied is how long it took them to understand the problem. Now, what occurred to me is you talked about getting inside the problem. There's very interesting data on that. There's a paper on that, and that's part of her dissertation. And I think that they were trying to understand the problem for 30, 45 minutes. Because we don't interpret it for them, we just present it, and it's up to them. So that maybe is the parallel that I think is really important. It's sort of sad, you say that we have these open-ended tasks, and then we've watched them go into the classroom, And we noticed that the teacher wants to be sure they understand the problem. And all that time is taken to be sure they understand the problem, but that really isn't giving it to them to own it. And I like that term, to get inside of it.
I think in philosophy of education, it's called feeling through, which I thought was such a nice term, feeling through.
Hi, I'm not sure this is a question, it may be a statement, I'll try my best. As we were watching the videos, it was apparent that the students were exposing each other to their own bag of tricks as far as the reasoning skills. And I was wondering if you noticed any sharing of learning styles across the groups.
I'm not so sure I know what you mean by learning styles, but there was sharing of ideas. I mean, it's very hard. You've got to pick a clip to show something. And if you even go back to that clip of the 4 children, if you look at that, the larger clip, or if you look at the full video, the various ideas were shared. And if you also look at the extended one of the various ideas are shared. If you looked at the last clip I showed you, they're looking at the taxi cab geometry, Jeff was summarizing. Remember, Brian said this, and Romina did it this way, and I did it this way. He was explaining the summary of the different ideas, but trying to point out that they all sort of came to the, as you very nicely put it earlier, Rebecca, we had different ways of getting there, but we got there. So I think it's hard to show in a clip, but that's really an important point. The sharing is extremely important, the listening. In their own voices later they say it's really important to listen to the ideas of others and to build on them, to grow. Now there are some sub-studies within our research. Another example of the children working on trying to look at the way this animal grew. And one of it was Tim Sweetman's doctoral dissertation was looking at the ideas that were presented and to see how the ideas were traced. He traced them to see if they were dropped, if they were built on, and what happened to any idea that came forth. That was an amazing dissertation. He had to study 39 videotapes and to track all of that anytime an idea came up. It's a very interesting study. You might want to look at it, and there are some papers. But that's important.
Thank you very much.
When fostering argumentation in museums, especially among visitors and students, how do we balance this with museums' traditional place as a sacred, safe place, presenting a well-known, well-taught argument or position to the public? And how do we balance argumentative exhibits and possibly argumentative visitors with the reverential and hallowed hall of museums?
I feel like I'm not sure the answer will match the question, but I think we might want to separate the word argumentation from arguing. So I think the idea behind argumentation is that students put forth ideas and back them up, or visitors put forth ideas and back them up, and that other people can then have other ideas and back them up. And by backing them up with evidence, you think about how you know what you know, and you begin to be open to perhaps other ideas because you can see, oh, this person knows this because they're looking at this information. How you balance that with museums as a safe space, I guess the question would be, are museums a sort of safe and sacred space because there's no disagreement in them, or for other reasons? I don't know if other people here have thoughts on that. I guess I never really thought of those as opposing, but it's a really interesting thing to think about.
I think something that's really wonderfully interesting is that I think this may be a very profound opportunity for some place like the Smithsonian, because when you think about critical thinking in math, it's very obvious. But when you think about critical thinking in history, culture, art, and all of our disparate units, what is the unifying factor that we can get at that becomes a curriculum element? I work with teachers and Discovery Theater, so I'm not one museum, I'm everybody's museum. So to think in terms of looking for pattern or matrix, or and getting at that from different places may be an overview that all of our units could focus on as if you were thinking about multi-visit, multi-museum visits. Why couldn't we, or could we, find something that is a question that would apply everywhere across all of the disciplines that would encourage discussion and looking for the same kind of patterning that would encourage a critical thinking across all the disciplines. I mean, it seems like a really great opportunity for us all to look at a large question in specifics, which is what the children did. They went from the specifics to the larger universal questions. So if we are going to design our system of visits, perhaps we go the other way and look for the larger overarching question that we want to get at through all of our various specifics. And then that's huge. It would take us all thinking very differently, though, I think. I mean, is that a possibility at a place like the Smithsonian is a big question.
I think that's a really interesting thought, and I think questions are amazing. And there's a book that's on the bibliography that we put out that's Neil Postman, Teaching as a Subversive Activity. And one of the things that he talks about in the book is sort of these big questions that are interesting. Because why do you want to be sitting in the museum or in the classroom thinking about boring questions that someone knows the answer to? So I think the idea of starting with that question is great. One of the things, as I was preparing for this, I was trying to talk to people from different institutions and different disciplines. And I think people approach questioning very differently. And so one of the things that would need to happen for a collaboration across disciplines is to think about how you approach an object and what kinds of questions you're asking, and to think about, do those need to somehow come into alignment to be teaching the same skills, or can you be using really different strategies? Are you essentially teaching the same skills anyway? And that's something that I'd be curious to know more about. And whoever asked that question disappeared back into the audio. Oh, there.
Carolyn, your study took place over many years, and the students learned to go deeper and they came to the answer themselves. And these are skills that are certainly not taught in our schools. You suggested that these kinds of skills might be taught in an after-school program. Do you think they are skills that we could possibly work towards integrating into just a regular classroom without your sort of intervention?
Children bring ideas, but they need an opportunity to be able to explore, to share, to communicate, and to test, to hypothesize, to produce evidence backing. And I don't think it matters what the content is or where it is. I think that we forget. I think if we need to remind ourselves that even very, very young children have very, very big ideas and capabilities and this ability to reason and think. It's a question of what's the opportunity and what's the context. How can you build upon it? How can you take advantage of what is naturally there? I talked about this study, but we have other smaller related studies, and there are other work that other people have done related to this, where they've started with older groups of students and other populations, but we find the same thing. I mean, what takes the time is you have to sort of believe and trust in them. It's sort of whether or not you're going to tell them how to interpret this painting or what was intended in it, they're going to still think their thoughts. And it would be nice to have those thoughts and ideas made public so that they could be discussed. Because if they're off track in their ideas, if they're way off, or if they're not producing good evidence or justification, we sort of owe it to them to have a chance to engage with others to see that. So I'm not so sure it matters. I don't think it's either math or science, or it seems to be easier in other areas because, mathematics is supposed to produce certain kinds of knowledge and reasoning. It would seem to be easier to me to be doing it in fields other than math and science. But it's up to you all to decide. And I certainly believe classroom teachers can do it, and many of them do.
Hi. You mentioned that you thought one of your ideas was allowing people the time to think when they're at museums, and instead of planning on seeing a whole exhibition, you would see 5 objects. I think that's a really interesting idea, and I was wondering, how do you get students, and especially young children, excited about coming to just see several objects, or even convincing curators to design exhibitions that are going to have just a few objects and allow that time to think?
I think that it's not, kids don't yet have the expectation that they're going to see a whole exhibition. It's really the adults. So I don't think it's actually convincing the kids. It's convincing the teachers or the average visitor who drops into the museum. So from the educational point of view, I wonder, for example, about having some sort of self-guided tour or even an audio guide. You know, people use these all the time to sort of move through the museum, and could you have these sorts of scavenger hunts that only go to 4 or 5 objects, so people would feel like they'd had an experience that was a completed experience, but that didn't involve seeing an entire exhibition. In terms of convincing the curators to do smaller exhibitions, are there any curators here? Oh, and they left. Shoot. I mean, I think educators and curators need to be talking more, and especially in art museums, this is a huge issue, but I don't think it's just art museums. I think it's a lot of kinds of museums, and I'm not sure what the answer is for that. I mean, I suspect actually that a lot of curators might be interested in doing smaller exhibitions. And at the Guggenheim, we'll often have smaller exhibitions in our side galleries, but then you'll have 20 objects crammed into one room. It's the economics of the museum that's not putting 20 objects on the ramps, where you would have the sort of type of, you know, experience where you'd have an entire bay dedicated to a single object the way you did in that picture, which is what Frank Lloyd Wright originally envisioned, was like Kandinsky all by itself and some stools. So I don't know how we convince curators, but or museum directors, I think it's more.
And does it have to be an either or?
To just have, you mean
Right,
a few objects or a lot? Yeah.
I mean, you could do it within what you usually do and try that as well and see how that works.
Mm-hmm.
I would like you to think seriously, as you have carefully, about what you do about once the student is in the museum. It seems to me we also need to consider something about how to get him there. Many teachers have a great deal of interest, but not necessarily the money to hire the bus and to get the children to the museum. And if an institution as important as the Smithsonian could consider having an item in its budget that might help those schools that need it to get to the museum, would be a novel idea.
That's true.
I'm wondering what you see as the future course of research along these lines, like for people interested in building on your research or for yourselves, like what topics you see coming out of this, what research you think should be done in the future?
Do you want to take that first?
Well, I think that a creative research agenda would be to really think what's possible in informal settings. I do think there is the natural motivation. Of course, there's the problem of how do you get students there to bring them to the museum. But even for those who do get to come and get there, that I think there's lots more that can be done informally that is not part of regular school, that's not going to be tested, that really sort of taps into the natural inquisitiveness of learners. And so I'd like to see more done in informal learning. There's really not a lot done. I think that's an important agenda for the future. Not just museums, but other places as well.
I think it would be really interesting to know how many visits you need to cultivate these kinds of skills, and I don't know exactly how you set that study up. But whether it can be done in 1 visit, 3 visits, 5 visits. And then to know whether, for example, 5 visits to a museum are cultivating critical thinking skills compared to other programs, because one of the things that you hear talked about sometimes is that it doesn't matter what students do, it just matters that they're engaged with something. So it could be chess in the schools, it could be a sports program, and I think there's some truth to that, but it would be very interesting to see if there's something specific that museums do. And Stephanie Norby, who introduced this program, was mentioning at lunch that when they brought principals to the Smithsonian and led them through a number of activities or experiences in the museum, and then they asked them what they think this could offer students, one of their answers was critical thinking. And so to think about, is there really something about that encounter with the original object and looking at it carefully and thinking about it carefully that's accomplishing something that's not happening somewhere else? So those are a couple areas.
I just had a question, and maybe this was on your website, but I'm a high school social studies teacher, and I was watching some of the things that you were doing up here with these students, and I was just wondering, how are these students chosen? Do you have to talk to their parents, I'm assuming, first, and get their approval? And being that I just was listening to a few comments coming out here, too, in regards to the way students think, I know I can often speak, I do a lot of activities in my classroom where I try to get them to think at a higher level. And students from elementary on up are taught not really to think, but they're showing, this is how you get the answer, this is what we're looking for. So did you run into any problems along those lines? Because I know we're running into them right now in education.
Well, I hear two questions. One, in the original design of the study, the students were selected randomly. They were randomly assigned to each of 3 first grade classes, and we followed one class for 3 years. And then we got much larger funding, but the students separated, they weren't together. That was unique in that school, but they were a random selection of students from a working class community. Now your second question, I think, is a little different. It's always, I've taught at a variety of levels. I've been a high school teacher, a college teacher, and I've been in lots of elementary classrooms with my research, and everyone always says it's the group before that, sort of gets in the way of what they could do in that level. And there are habits. They're not the habits that maybe are not your ideal in terms of the kinds of ways you want your students to approach problems. But I do think those habits can change if you, sort of persevere and have different expectations. If you establish this different culture of expectations. It takes time, but you have to be stubborn about it. I had a graduate student who taught at a 2-year college and said, no way could her students engage this way or do this or work on. They just want the answer, want the answer, want the answer. Well, it ended up that she studied this. She studied 3 groups of students over a couple of years and wouldn't show them how to do the problems, really put it back to them, their groups, they're working it, produced a wonderful study, and her students did really quite nicely. She even wrote a paper comparing the kinds of reasoning in contrast to the reasoning that was exhibited with the students in our longitudinal study. And we're finding, even starting with 6th, 7th graders, middle school children, in settings that they're not supposed to be at all motivated, and that they eventually, when they work into the culture. You should just insist on it and persevere. So I think you should be optimistic. Of course it's harder. It is nicer once that's the case, and it takes time, but it's doable. And, maybe imperfect, but yet better. So you ought to set, reconsider your expectations a little bit too. I don't know if that helps or is encouraging enough for you.
I think that will be our last question, and I would like to take a minute to thank both Rebecca and Carolyn for joining us today. Thank the audience. A number of the questions gave me a lot to think about, and I hope we're able to continue those conversations. I was particularly intrigued by the idea of ways that we might think of larger questions that would transcend multiple visits to the Smithsonian. So hopefully we can find ways to continue to talk about this and work together. Thank you for coming today.
make sure I don't mess anything up. Just pull.